Okay, so this class we are going to discuss infinite series with positive as well as negative terms. So in the previous two classes we discussed about series with positive terms, and then we discussed convergence of series with positive terms. Okay, there are some tests in that: comparison test, ratio test, Cauchy nth root test, and then integral test. There are some more tests are there: logarithmic test, RAPS test, all the things. Okay, here we have few more tests to check an infinite series with the positive and negative terms of the series. Okay, so first we define what we mean by absolutely convergence. When we say a series is said to be absolutely convergent, so definition: suppose we have a series summation an is said to be absolutely convergent. Is said to be absolutely convergent. Absolutely convergent. If we take the series of modulus of an, if it is converges, then we say it's absolute convergence, is convergent. So each an's are maybe positive or negative. When we say that series is absolutely convergent, if we take the modulus of an, if the series is convergent, we say it's absolutely convergent. Again, another definition: when we say a series is said to be conditionally convergent, if the given series is convergent, but if we take the modulus, that is divergent. So another definition: a series is said to be conditionally convergent. A series is said to be conditionally convergent. Conditionally convergent. If it is convergent but not absolutely convergent. But not absolutely convergent. Okay, so we will discuss some examples. Okay, now there are some theorem. Every absolutely convergence is always convergent. Okay, so why that is true? So theorem: every absolutely convergence is convergent. Absolutely convergent is convergent. So absolutely convergent is what? If we take modulus of that an, that should be converges. So that is trivial, right? You can easily prove it. Suppose if we take some summation an, okay, is given series, assume that this is absolutely convergent. That means what? Modulus of summation modulus of an is convergent, right? And we know that even this an is positive or negative, but an is always less than or equal to modulus of an, right? Because modulus is a positive number. Therefore, we know that by comparison test, given that this this series is convergent, therefore by comparison test, summation an is convergent. Okay, so every absolutely convergent is convergent, but the convergent series need not be absolutely convergent. The converse need not be true. We will discuss that example later. Okay. Now, that important theorem that is called the Leibniz theorem. Before that, we define what is alternating series. So, alternating. So, that is alternatively we have a positive and negative terms. Alternating series. So, how the alternating series is of the form? A series is of the form is of the form u1 minus u2 plus u3 minus u4 and so on. Okay. So the nth term is maybe minus 1 power n minus 1 un. Anyway, so alternative, the coefficients are plus minus, but all the ui's are positive. That is, un is greater than or equal to 0 or strictly greater than 0, better take. All the un's are positive, but the coefficients are alternately plus 1 minus 1. Such a series is called alternating series. Okay, this is for every n. In n, a series is also from this is an alternating series. Alternating series. Now, usually, simply we denote this series by the summation notation, summation minus 1 power n minus 1 into un, where n equal to 1 to infinity. If substitute n equal to 1, minus 1 power 0, that is nothing but 1, we get u1. Substitute n equal to, we get minus u2 and so on. Okay. Now, when this alternating series is convergent, that is a theorem. The Leibniz theorem says when this alternating series is convergent. The theorem is called Leibniz theorem. Leibniz theorem. So the Leibniz theorem guarantee that the alternating series is convergent. So what is the assumption we need? Suppose we have a sequence of positive number and then consider the alternating series. So let the sequence un be a sequence for any n. Okay. So this sequence satisfies the condition. The first one is all the un's are greater than or equal to 0, should be positive. For any n in n, all the members are positive. And the second condition is it should be decreasing. That is, un plus 1 is smaller than un for any n. That is a decreasing sequence. And the third one is the sequence converges to 0. That is, un converges to 0 as n goes to infinity. If such a sequence satisfying these three conditions, then the alternating series that like minus 1 power n or n minus 1, you can take anything, into un summation n equal to 1 to infinity converges. The alternating series is convergent. That's it. So therefore, you have to check three conditions. First one is all don't take the coefficients. You have to take only the un's. If all the un's are positive and they're decreasing and then converges to 0, then the alternating series is convergent. So this is Leibniz theorem. Okay. Now we solve some problems to check some alternating series converges or not using this Leibniz theorem. So this is a very important theorem in the alternating series. Okay. Even you can say this is the only theorem, maximum we are using this theorem to check alternating series converges or not. That is not if and only, but this is a main theorem. So for example, if you consider this alternating series, summation minus 1 power n plus 1 by n equal to 1 to infinity or 0 to infinity, you can take anything. It's not an issue, because even if you start with the minus term and then plus minus and so on. Okay. So if you expand this, actually what you'll get, if substitute n equal to 1, you get minus 1. It will be n equal to 2. Okay, sorry. If you take n equal to 1, we get plus 1. Okay, 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 and so on. So this is a series. And already we know that the harmonic series just 1 by n is diverges. Already we know that this is divergent sequence. But if you take the alternating series minus 1 power n plus 1 by n, we have to check is convergence or not. Now in this case, what is our un? Un is nothing but just the 1 by n. Now clearly the first condition is satisfied because all the 1 by n's are positive. Therefore, it's greater than or equal to 0 for all n. Because if you give any values of n, you will get always positive number. Now, the second one is, since we know that n is smaller than n plus 1. Sorry, n is smaller than n plus 1 implies that if we take this n plus 1 this side, we get 1 by n plus 1 strictly less than 1 by n. So, what is 1 by n plus 1 is nothing but that is un plus 1 is less than, we can write less than or equal to. Okay, that is not issue. So, this is always true for any natural number. Therefore, this un satisfies the second condition also. Now, the third condition clear, 1 by n converges 0, right? Therefore, the un is nothing but 1 by n is converges to 0 as n goes to infinity. Therefore, by Leibniz theorem, we have a Leibniz theorem. This alternating series summation minus 1 power n plus 1 by n is convergent. Now, it is absolutely convergent or not. So, absolutely convergence is what? You got to take modulus of all the things. So, consider the modulus of the entire thing minus 1 power n plus 1 by n modulus. Modulus of minus is plus. Therefore, simply we get just 1 by n. And we know that this is divergent. So, the series is convergent, but it's not absolutely convergent. Therefore, this is conditionally convergent. Conditionally convergent series. Because the original sequence converges, but if you take modulus, that is diverges. Okay. So, this is an example of the previous theorem. What the previous theorem says, every absolute convergence is convergent, but the convergent series is not absolute convergence. So, that is an example minus 1 power n, minus 1 power n by n. This is a standard example.
Sir, we cannot find to what number it will converge, sir.
Yeah. So, that if you want to know what is the exact value, you have to take the partial sum and then you have to find the limit of that partial sum, that is the value. Here, but the question they will ask, maximum they will ask is convergent or not. They will not ask what is the sum. Okay, suppose they are asking sum means you have to take the partial sum, that is Sn. First n, you got to simplify and then find the limit of the sequence, you will get the value. That is the limit of, that is the sum of the sequence series. So, maximum they will ask the convergent or divergent. Okay. Now, next problem we can discuss. So, next alternating series summation minus 1 power sum n minus 1 n square by 1 plus n factorial. Okay. Now, we have to check it is absolutely convergence or not. So, that is a question. Okay. So, therefore, absolutely convergence means what? You have to take the modulus. Therefore, this is cancelled. We get only summation n square because n is a thing positive. Therefore, n plus 1 factorial. So, is this convergent? Therefore, what is un? So, you have to apply ratio test. Un is n square by n plus 1 factorial. Therefore, un plus 1 by un is n plus 1 square by n plus 1 plus 1 n plus 2 factorial into un. Therefore, we get n plus 1 factorial by n square. So, we can take n outside from the first term. Therefore, we get 1 plus 1 by n whole square and then we have n square. We can write into n plus 1 factorial. So, n plus 2 factorial can be written as n plus 2 or n plus 1 factorial into n plus 2, okay, into n square. Now, we can cancel n square and then n plus 1 factorial. Now, what you get? We will get 1 plus 1 by n whole square by n plus 2. Or I did any mistake? Okay, n plus 2. Now, as n goes to infinity, this goes to where? In the numerator, we have 1 because 1 by n goes to 0, 1 plus 1 by n goes to 1. But in the denominator, it goes to 0, 1 by n, because it is like 1 by n plus 1, n plus 2. Therefore, it converges to 0. But 0 is less than 1. By comparison test, this series is convergent. Since this series is convergent, therefore, this given series is absolutely convergent. Is absolutely convergent. Because we consider the modulus of the given series. It is convergent, therefore, it has absolute convergence. Okay. The question is, you have to check this absolute convergence or not. Okay. But the question is not, you have to check the convergent or not. If you want to check is convergent or not, you have to check this un satisfy the 3 conditions or not.
Sir, this series is absolutely convergent, no, sir? Then we can use that theorem.
Yeah, convergence always convergent. Yeah, the theorem says every absolute convergence series is convergent. Yeah, good. Now, next problem. Suppose the series contains some unknown value. They ask for what values of x the series is converges absolutely. Exercise 3. Suppose if you consider the series x plus x square by 2 factorial plus x cube by 3 factorial and so on. So we have to show that this converges absolutely for every values of x. So actually show that this series is converges absolutely. Absolutely for each x. Then actually what we have to prove, so what is the nth term? Un is x power n by n factorial. Okay. So by therefore, since given that we have to show that this is absolutely convergence. Okay. Now what is the modulus of un plus 1 by un? Because we are going to consider this series now. Okay. But we don't know these uns are positive or negative because we don't know what is values of x. If maybe x are positive or negative, so better we take modulus of. We have to check this series converges or not. So again, you have to apply the ratio test for these terms, modulus of un plus 1 by modulus of un. So therefore, what you will get? Modulus of un plus 1 by is nothing but modulus of x power n plus 1 by n plus 1 factorial. N is a natural number, therefore that is positive, therefore no need to write modulus, therefore n plus 1 factorial into by un, therefore we have n factorial in the denominator we have a modulus of x power n. Now again simplify this, modulus of AB we can write modulus of x power n into mod x, right? And this is n factorial divided by n plus 1 factorial can be written as n factorial times into n plus 1 into modulus of x power n is nothing but mod x power n, because modulus of AB equal to modulus of A into modulus of A. You can cancel these all the things. So finally in the numerator we have mod x, in the denominator we have n plus 1. Even since mod x is just a constant, therefore this approaches to 0. Since this value is less than 1, therefore since this quotient the modulus of un plus by un is less than 1, therefore this series is convergent. Because if you take any values of x, even if you take x equal to 0, we get 0 sequence. It's always converges 0. If you take positive value, again it converges to 0, because we have in the denominator we have n, therefore it takes to 0. Therefore it converges absolutely for any values of x. Okay. Sometimes we will get some series, the sequence, the limit point, sometimes we will get mod x, sometimes. Okay. In that case, you have to write it is absolutely convergence only for values of x or modulus of x is less than 1. But in this case, we can take any values of x. This is absolute convergence. Okay. Now maybe I'll solve some more problem, but you have to say for what values of x the given series is converges. Okay. Fourth problem like that. Suppose prove that the series x minus x cube by 3 plus x power 5 by 5. Alternative plus and minus, but only the odd terms converges. Suppose is converges, we have to prove if and only if the x lies between -1 and then +1. So how to prove this one? So suppose assume that, so now what is the nth term? Therefore the given series is summation -1 power n plus 1 or anything, n minus 1 or anything, into x power n by n. Okay. So if substitute n equal to 1, you get the first term. If substitute n equal to 2, you get the second term and so on. Therefore, our un is just this x power n by n. If you consider this alternating series, this is our un. Now we assume that this series is converges. So if it is converges, then how to find this x?
Sir, for n is equal to 2, it will be x square by.
Okay, sorry, then n plus 1. Then okay, sorry.
2n plus 1, sir.
2n minus 1 by 2n minus 1. Or 2n plus 1 by 2n plus 1, you can take anything. Okay, good. So now you have to take the modulus of un. So we can consider this is entirely, this is or you can take, don't bother about this -1 because we don't know what is the values of x. We have to prove that x lies between -1 and +1. Therefore, modulus of un is nothing but modulus of x power 2n minus 1 by 2n minus 1. And then again write what is un plus 1. Modulus of un plus 1 is, you get a x power 2n plus 1, 2 and then 2n plus 1 by again 2n plus 1. So this is a un plus 1. Now find the quotient. un plus 1 by un or un plus 1 by anything. So modulus of un plus 1 by modulus of un. So you will get a x power 2n plus 1 by 2n plus 1 into x power, modulus of modulus of this into un. Therefore we can take 2n minus 1 by modulus of x power 2n minus 1. So this 2n we can rewrite as like this. So we can cancel this we can write this is a x square. Okay. So modulus of x 2n minus 1 plus 2. We can write this plus 1 as -1 plus 2. If you sum this, you will get this one. So into 2n minus 1 whole divided by 2n plus 1 into modulus of x power 2n minus 1. So therefore 2n minus 1 cancel. We have modulus of x square, the first term. And if we take 2n outside and then we can cancel from the numerator denominator, we get 1 minus 2 by n. And then denominator also we have a 1 plus 2 by n. Sorry, 1 by 2n. You take 2n outside and then cancel it. Now as n goes to infinity, this goes to mod x square. Right? So it is given that it converges. Therefore, it should be less than 1. Since mod x square is less than 1, therefore mod x also less than 1, because mod x is a positive number. Okay. Since mod x is less than 1, therefore we can write -1 less than x less than 1, strictly less than 1, strictly less than x. But we have to show that even if we take x equal to 1 or x equal to -1, that even that series is converges. okay, y. So now we found that the lower bound and upper bound. So but what we have to prove? We have to prove that x also takes -1, x also takes +1. So putting x equal to 1, suppose if mod x equal to 1. So now finally we prove that summation modulus of un is convergent if that mod x is less than 1. If mod x equal to 1, then what will happen? So if mod x equal to 1, so that means what, there are two cases, even x equal to 1 or x equal to -1. So therefore this is a case means what, either x equal to 1 or x equal to -1. In this case, if substitute x value equal to 1 in the given series, then what you'll get? So just you get 1 minus 1 by 3 plus 1 by 5 minus and so on. So general so and so on. So therefore this is alternating series, right? So what is the nth term? Minus 1 power n or n plus 1, 1 by 2n minus 1. So this is the nth term. You can easily check that this is our un now, the new or un or vn. This is always positive for any values of n and then decreasing as converges to 0 by Leibniz theorem. This is converges. Therefore, if we take x equal to 1, this is converges. Therefore, we can allow to take x equal to 1. Now, similarly, if you substitute x equal to minus 1, so again look at the series, everything is a odd power. Therefore, this is odd power, we get plus, and this is odd power, we get a minus. So again, the only thing is nothing but you have to take minus outside, we get the same thing, minus x plus minus plus. Okay, but the given series start from plus minus and so on. But now we get a minus plus minus plus and so on. So it will not just only the sign changes. Okay. So if you say, if you take x equal to -1, you will get the series -1 plus 1 by 3 minus 1 by 5 plus 1 by 7 and so on. So still again, this is a alternating series. We can write, instead of take n plus 1, just to take the power n into 1 by 2n minus 1. That's it. Again, we are taking only this. This is always positive, decreasing, and then converges to 0. Therefore, this by Leibniz theorem, this is converges. Even for x equal to minus also, this series converges. Therefore, now we prove that this part. Therefore, this converges if and only if x lies between -1 and then +1. Okay. Now, we have another problem. Suppose some series contains cos, sine. So before that, you should know what is the bound for cos. So always the graph of sine and cos is always lies between -1 and +1, right? So therefore, modulus of sine x is always less than or equal to 1. Because if you look at the graph, it's always lies between -1 and +1. It's bounded by 1. Similarly, for cos x graph also is always bounded by 1. Or even sometimes they say it, modulus of sine x is always less than or equal to mod x. Okay. So similarly for for each x, if suppose we take x equal to 1, modulus of sine 1 less than or equal to mod 1 and so on. So similarly for cos, modulus of cos is less than or equal to mod x. But anyway, the maximum bound is 1. Okay. Now, maximum we use this bound for sine and cos. Now solve some problem. Test absolute convergence and then convergence of the series. Okay. Suppose if you consider the series -1 power n into cos of n alpha by n into square root of n. Okay. First you have to check absolutely convergence. If it is if it is absolutely convergence, we know the theorem it is convergent, right? So if we take modulus of these, then the minus cancel, we get modulus of un. Modulus of un is nothing but modulus of what is un, this entire thing, and then no need to write this -1 power n because always positive. Therefore, we get just cos n alpha by n into, actually n root n is nothing but n power 1 by 2. So already is n is here into n power 1 by 2 is nothing but n power 3 by 2. Okay. So therefore, n power 3 by 2. modulus. And we know that modulus of a by b is nothing but is actually equal to modulus of a by modulus of b. So therefore, this is equal to modulus of cos n alpha by modulus of n power 3, but n is a natural number, therefore modulus is same as the same thing. And we know that cos is bounded by 1. Cos of anything is always bounded by 1 by this. That's why I am writing here less than or equal to, because cos n alpha less than or equal to 1, the denominator this one. So this is true for any n. Now this sequence modulus of un is less than or equal to this vn, and we know that this is convergent, this series, because this is a 3 by 2 series. This 3 by 2 is bigger than 1. Okay, this is converges. By comparison test, this is converges. That is, the given series is absolutely convergence. That is, u modulus of un is absolutely convergence. By theorem, every absolute convergence is convergent, and hence convergent, and hence and the modulus of un is convergent. So you should know the bound of cos and then sine. So similarly, instead of cos, suppose I give some sine n alpha by n cube, you can easily show that this is a convergence series. Suppose if you take consider this series, alternating series, minus 1 power n sine n alpha n times alpha by n cube. Now we have to test whether the given series is absolutely convergence or not. So again, if you take modulus of un, you will get finally less than or equal to 1 by n cube. And we know that this series is convergent because this 3 is bigger than 1. Therefore, this series is convergent. Since this series modulus of summation modulus of un is convergent, therefore the given series is absolutely convergent, therefore it's convergent. Okay, that is very important. Now, another thing. Maybe we will do some more example. Okay, sixth one. So suppose we have a series in terms of log, that is log of 2 by 1, that is the first term, minus log of 3 by 2, plus log of 4 by 3, and so on, minus and so on. Now test the series converges or not. Therefore, what is un? Is nothing but log of the nth term, n plus 1 by n. So even we can cancel n, therefore we get log of 1 plus 1 by n. So that is a un. So therefore the given series is nothing but summation minus 1 power n plus 1 into un, where un is log of this one, where n equal to 1 to infinity. Okay. Now this is an alternating series. We have to check this un is positive or not. If substitute n equal to 1, log 2 is positive. If you substitute n equal to 2, log of 3 by 2 is again positive, and so on. So therefore, this log of 1 by n is always positive for any natural number. Therefore, this un satisfies the first condition. Now, we have to check this is decreasing or not. So therefore, we have to find the, we have to show that this un plus 1 less than or equal to un. Okay, that is what we have to prove. We have to take this un to that side. We have to show that un plus 1 minus un is negative. If you prove this, you can take this un, we will get this one. So now consider this un plus 1 minus un, and then we have to show that is less than 0. So un plus 1 minus un. Now un plus 1 is nothing but log of 1 plus 1 by n plus 1. Just replace n by n plus 1. Minus un is log of 1 plus 1 by n. Now we know that this is log a minus b, therefore this is nothing but log a by log b. So this is equal to log of a is 1 plus, okay, maybe I can again, if you simplify this, n plus 2 by n plus 1 by this number, again this is nothing but n plus 1 by n, right? I simplify this is nothing but n plus 2 by n plus 1. Now I can write log of, I can write actually n plus 2 by n plus 1 into n by n plus 1. Okay. Now you can cancel it, and then because numerator, from this you can take n outside, already n is there, therefore n square, denominator also you can take n from here, you can cancel n square. So finally what you'll get, therefore log of, in the numerator we have just 1 plus 2 by n. The denominator actually n plus 1 whole square, therefore we get 1 plus 1 by n whole square. Okay. Now what will get? I'm writing right? Correct, right? So now maybe before that, so we know what is the value of log 1. Log 1 is 0, right? So suppose the log of this number is lies between 0 and 1, then should be negative. Okay, so suppose if you take 1 here, so log 1 value is 0. Okay, if you look at the graph of something 0, this, if you draw the graph of log x, if you take the graph at the point 1, it gets 0. Now what about this interval? If you take negative, actually the graph may, the log x graph may be, I think, goes this way. Okay, so for within this 0 to 1, the graph is negative. So that's why first you have to check this number is less than 1, and anyway it's positive because everything is natural number. So first we have to show that this is a number lies between 0 and 1, then log of this number is negative. Therefore you can take u1 to that side, we get increasing. Now the only claim is you have to check this n into this, so n into this divided by n plus 1 whole square. We have to show that this is less than 1. So we have to prove this less than 1 means work backward. So the suppose assume this is true. Now n square plus 2n is less than n plus n square 2n plus 2, sorry, plus 1. We can cancel n square, we can cancel n, so we get a 0 less than 1. Yeah, it is true. Yeah, it is true. Okay. So this number, log of this number is lies between 0 and 1 because always positive. Everything is a natural number, is always positive. Okay, so whenever we have these, since log is an increasing function, therefore that's the positive side, therefore we take log of this less than or equal to log of 1. Log 1 is 0, therefore this log of this is negative. So therefore we say we give a increasing. Now we say this un satisfy the second condition, and then as n goes to infinity, what this un goes to is 0, because this 1 by n goes to 0, therefore log 1 value is 0. Therefore this un satisfies the three conditions of Leibniz theorem, therefore this series is converges. Okay, this series is converges by Leibniz theorem. Any doubt in this? Okay. Now we have already I mentioned that every absolute convergence series is convergence, but converse need not be true. Already we discussed that minus 1 power n, that is a standard example. Okay.
Sir, how is this a decreasing sequence, sir? Log value is less than 0.
Now we what actually, so un, we start from here, right? Un plus 1 minus un is negative. This is less than or equal to 0. You can take un to that side, we get this one. Un plus 1 is less than un. That is a decreasing. So substitute n equal to 1, you get u1 is bigger compared to u2, and then this is compared to u3, this is bigger, and so on. So it's a decreasing. So we got to find the difference between the n plus 1th term and the nth term. If it is negative, then it's a increasing, it's a decreasing. Suppose this un minus un plus 1 is less than or equal to 0, it's a increasing. Yes, you got to take this type. That's it. Got it or not? Still any doubt?
No, sir.
So okay, then we have some another theorem. Suppose we have a series and then some sequence. Suppose if we take the product, it will converge or not. That is theorem called Dirichlet's theorem. Okay. And then we can say easily. Okay, so that is a very important theorem. The theorem is called Dirichlet's theorem. Dirichlet's theorem. So what the theorem says, suppose we have a monotonically decreasing sequence un or an. So suppose we have a two condition. Let the first one is, suppose if we take some un be a sequence, be a positive monotonically decreasing, be a positive monotonically or decreasing, monotonically decreasing sequence, with the limit 0. That is, this un converges to 0, with un converges to 0. Suppose we have one decreasing sequence converges to 0, but everything is a positive. All the uns are positive. And suppose we have a series, summation an, be an infinite series, summation an n equal to 1 to infinity, be a series. Okay, be a series. But we don't know this is converges or not, but its partial sum is bounded. A series such that its partial sum Sn is bounded. Its partial sum, the partial sum sequence, okay, the sequence of partial sum, otherwise sequence, its sequence of partial sums is bounded. Then the theorem says the product of summation un an is convergent. Then the series summation un into an is convergent. N equal to 1 to infinity. Okay. Suppose if a given series is a product of two sequence, that means maybe you have a product of two nth term. Okay, 1 by n into n plus 1 like this. So we have to choose something is un, and then you have to check this is monotonically decreasing or converges to 0 or not. And then the series an whose partial sum is bounded, then we can directly say that this is converges. Okay. Now another theorem, actually we have Abel's theorem, we have obtained from this theorem. Okay. So in the Dirichlet's theorem, we are not mentioning that this given sequence an is not convergent. Okay, just a partial sum is bounded. The Abel's proved that just you can assume that the an is convergent, the summation an is convergent series, then the product is convergent. Okay, that is a thing. So Abel's theorem. So there is a slight difference between this Abel's theorem and then Dirichlet's theorem. But Abel's theorem is obtained from Dirichlet's theorem by some weakening some condition. We have to weak some condition on un also. So what here even they given that strictly decreasing with converges to 0. Suppose if you omit this condition un is converges to 0, then what will happen? So that is a weaker condition. Okay. So Abel proved that suppose if you take a decreasing monotone decreasing sequence, okay, maybe it converges to 0 or not converges to 0, then still the product is product series converges. Okay. So the first same thing. So let un is a positive monotonically decreasing sequence. Decreasing sequence. Just decreasing, that's it. No need to converge to 0 or anything. Just a decreasing sequence. And the second condition is the summation an is convergent, but Dirichlet assumed that the partial sum of this series is convergent. Sorry, bounded. But here he assumed that is convergent. If it is convergent, we know that the partial sum is bounded. Okay. Every convergence, if you take any convergence sequence, the partial sum is convergent, then every convergence sequence is bounded. Therefore, yes, partial sum is bounded. We will get. It's a convergence series, then the product is convergence. Then the product summation un into an is convergent. So able that omit the condition un converges to 0 and they included the second condition, the convergence, the series is convergent, still the product un an is convergent. Okay. So this is Abel's theorem. Now we solved some problem on this. Okay. Using this Abel's theorem or Dirichlet's theorem, using either both of this. Example. So suppose if you consider the series, test whether the series converges or not. N cube plus 1 power 1 by 3 minus n whole divided by log n. So this is a given series. Now first you have to choose un and then an. Because this is nothing but product of two series, we are going to use Abel's theorem or Dirichlet's theorem. Therefore, we need a un and then an, and then un should be decreasing. Maybe converges to 0. If suppose you want to use Dirichlet's theorem, the un converges to 0 as n goes to infinity. Now, can anyone tell me which one is an, which one is un? Anyway, one of the sequence should be converges to 0. Should be decreasing and then converges to 0. Okay, so don't use the same notation. No need to use the same notation. Un is strictly decreasing. You can take anything, but one of the thing converges to 0. The sequence converges to 0. One of the series is convergent or the partial sum is bounded. Suppose I am taking un is this thing, or you no need to take anything. So if you want to use the same notation, use the same notation. I am taking un is 1 by log n. And then an is n power 3 plus 1 power 1 by 3 minus n. Now this un is a sequence. This is a decreasing clearly, because if you take log n plus 1, 1 by log n plus 1 is smaller than 1 by log n. Okay, therefore it's a decreasing. As n goes to infinity, log n goes to 1 by log n goes to 0, because log infinity, the denominator we have infinity, 1 by infinity like 0. Therefore, this un satisfies the condition of Dirichlet. Okay. Now look at what the condition we have to check. This series is converges or not. The summation. Otherwise, you can take the partial sum. Okay. So first you have to simplify this an. You can take something outside, and then if possible you can take outside. So therefore, in an equal to, if you take n cube outside from this, so actually n cube plus 1 power 1 by 3 minus n. So from the first term you can take n cube outside, n cube and 3 cancel, we have n, and still you can take n into 1 plus 1 by n cube whole power 1 by 3 minus n. Okay. So anyway, both term contain n, you can take n outside. We have this minus 1, 1 plus 1 by n cube power 1 by 3 minus 1. Okay, now we know the formula for 1 plus x power p by q. Okay, you can use that formula. I directly write this one. So what you'll get, if you apply x plus y or 1 plus x power p by q, okay, for any rational we can use. Okay, Bernoulli's equation says 1 plus x power n, but even you can apply for any rational number p by q. Okay, you can look at the formula. Now I directly write, this is nothing but if you simply use the formula, expanding this by binomial thing, you get 1 plus 1 by 3 n square, that is 1 by I think p into q, p by q into this n cube plus, sorry, minus, alternative should be minus plus. One by 9 n power 6 plus and so on, minus this one, and this 1 cancel. If you multiply n inside, we get 1 by n cube, sorry, 1 by 3 n square minus 1 by 9 n power 5.
Sir, if it's alternating, then second term should be negative, no, sir?
No, actually the formula starts from 1 plus something. After that you get minus. So just to go through the formula, I think I forgot that exactly. So you can find in the net. So for any rational number, we can write the binomial expansion. Okay. You just to go through it, you will get it. Okay. Now anyway, we get this an is nothing but this. Now we can say that this, I am going to show this an is convergent or not. Okay. So I'm going to use I'm going to choose some other element bn sequence. From this I guess that 1 by n square we can choose. Now look at what is an by bn. So what you'll get, an is actually we get the denominator, right? Sorry, otherwise, yeah, you can take an. No, what you'll get, actually you are in the, we have bn is 1 by n, so therefore you have a n square. That is, otherwise you can write n square times this an. So that is because 1 by bn, therefore we get n square times the things 1 by 3 n square minus 1 by 9 n power 5 plus and so on something. Now if you multiply inside this n square, n square, n square, so the first term we have a 1 by 3. All other terms are the denominator always power of n. Now what is the limit? This goes to 1 by 3. It's a non-zero number. For the ratio test, sorry, in that if we get some an by bn values, non-zero value, both have same behavior. Now the series summation bn is convergent because the power is the 1 by n square series converges. Therefore, an is, or summation an is convergent.
Sir, can't we apply the limits directly to an, sir?
But we need series. We have to check that the series is convergent. But if you apply n equal to infinity in an, what you will get? You get 0. From that, what you can say? The sequence may be convergence to 0. The an sequence converges to 0. The nth term converges 0. From that, we cannot say the series converges or not. Anyway, nth term converges 0. Okay, but the series may or may not be converges. But we have some theorem that if you found some other bn, if the ratio an by bn converges to some point non-zero number, then both a and bn have a same behavior. Since we know about this bn is convergent, summation series, summation bn converges, therefore summation an is convergent. Therefore, now come to our problem. Actually, we can use the Abel's theorem. No need to check this un is converges 0 or not. Suppose you are trying to prove this Abel's theorem, we are using Abel's theorem. Now this un an satisfy the condition of Abel's theorem a and b. Therefore, by Abel's theorem, this is convergent. Because this is a product of two sequences. One is un, the numerator, 1 by log n is the another sequence, and then it satisfies the Abel's theorem. Therefore, we can prove that this converges by Abel's theorem. Even you can take that this is actually for Dirichlet's theorem also we can use, because now we prove that this un also converges to 0. And one more thing, we have to prove that the partial sum is kind of bounded. But if you want, you can use Dirichlet's theorem also. Okay, but you have to show that the partial sum is bounded. But proving this convergent also simple. Anyway, this is simple case of abelian. Both are almost same. Okay. Now this is a thing. Okay. Now there are some other theorems there. Maybe we'll discuss later. Okay. So almost we discussed the series things. So this is a very important theorem. Product, the Abel's theorem, all the things. And then another one is rearrangement. I think rearrangement is not in the syllabus. If it is there, we will discuss the next class. Okay.